Hi, guys. Okay, let's look at chapter 6, electronic structure and periodic property. This is from the book Open Stax, Chemistry, 2nd edition. And we are going to be looking at the learning check problems in section 6.1, 6.2, and 6.3, which relate to energy, Bohr's model, and quantum theory. Okay, so very first question is the 6.1, in which they have given us 850 megahertz. That is a frequency, and they're asking what is the wavelength in meters. So here we are being asked to find the wavelength, and when the frequency is given, and there are certain things we know. One is that the megahertz, 1 megahertz is equal to 1.0 into 10 to the power 6 hertz. That's one thing. Next thing is, what do we know about hertz? Hertz is seconds inverse. In other words, hertz means it's a unit, of course, of frequency, but it's per second, that is cycles per second. So we also write it as s raised to the power -1. That is the unit for hertz, or hertz is equal to that. Next thing we know is the speed of light. The speed of light is 2.99 into 10 to the power 8 meters per second. And that equals to the wavelength times the frequency. So C is equal to, so that's the relationship. C is equal to wavelength times the frequency. Now we are given the frequency, which is 850 megahertz, and we're being asked to find a wavelength. So here we already know the value of C. We are given the value of nu, but we need to find a lambda. So C is equal to nu lambda. Lambda is the wavelength and nu is the frequency. Okay, so this is frequency and this is the lambda, L-A-M-B-D-A, okay? And that is the speed or the velocity of light. Now, here in this relationship, you can find the value of the lambda by simple transformation, algebraic conversions, in other words. So you take C over nu is equal to lambda. Now, this we are going to use, this relationship we are going to use to find a wavelength. However, we need to first convert the value of our megahertz. So first, let's do this. The first strategy is or in other words, the first step is you take 850 megahertz and convert them to hertz. So megahertz is converted to hertz. And how do we do that? So we know that 1 megahertz is 1.0 into 10 to the power 6 hertz. Okay, and that is the conversion factor, 1 megahertz, and then times here 850 megahertz. So this cancels out the megahertz. This cancels out the megahertz. And you are left now with just the unit of hertz. Now this hertz can translate into seconds inverse. So when you do this calculation, it comes out to be, remember, 1, 2, you move two, the decimal has been moved 2 places to the left. So this becomes 10 to the power 2. So this is, in other words, 8.50 into 10 to the power 6 plus 2. So I just don't want to put it here. So this becomes 10 to the power 6 and 10 to the power 2 is added. So show this here, 2 plus 6. So this becomes 10 to the power 8, 10 to the power 8 hertz. Another way of writing this is 8.50 into 10 to the power 8 seconds inverse. Okay, so that is our conversion of megahertz to hertz, and then finally to seconds inverse, and that is what we need. So this is equal to s minus 1. Okay, so this is what we need. Next is the second step. The second step is here we will just substitute the values. So we know that C is equal to C over the frequency is equal to the wavelength. And wavelength, we need it in meters. So what is the value of C? C is 2.99, 10 to the power 8 meters per second. So write this down, 2.99 into 10 to the power 8 meters seconds inverse or meters per second over the wavelength, over the frequency, which is 8.50 into 10 to the power 8 seconds inverse. And this is equal to the wavelength. Now here, wavelength is equal to, I'll just write this again, 2.99 into 10 to the power 8 meters seconds inverse over 8.50 into 10 to the power 8 seconds inverse. So now seconds inverse and seconds inverse are cancelled out. 10 to the power 8 and 10 to the power 8 cancel out, and you are just left with 2.99. Divide that by 8.50 and meters. Okay, so this gives you, let's finish this calculation. Okay, so this comes out to be 0.3517. And as you can see, there are three significant figures here, so our answer should be three significant figures. And since 7 is more than 5, therefore 1 is rounded up. So here your answer is 0.352 seconds inverse, or meters. Sorry, this is in meters. So that's the answer. Okay, now let's look at the next problem. Okay, so the next question is calculating the energy of radiation. Here we are given the frequency, which is 3 into 10 to the power 9 hertz. And we are being asked to find the energy of 1 photon. So we know certain things. We know, first of all, the formula for energy, which is hc over lambda. H stands for the Planck's constant, and its value is 6.626 into 10 to the power -4 joules times second. The value of c, which is the speed of light, is 2.99, and you can also use 3.0 instead. So it's 2.99 into 10 to the power 8 meters per second. Now, the relationship between the frequency, wavelength, and the speed of light is c is equal to lambda nu. So c over the frequency is equal to lambda. So here, this is what we are going to find. Why do we need this? First of all, we are given the frequency. So we need the wavelength in order to compute it into this formula. Okay, so E is equal to hc over lambda. So here, what do we do? So we are going to, first of all, find out the wavelength. And that is, the wavelength is equal to c over nu. The c is 2.99 into 10 to the power 8 meters seconds inverse, or meters per second, over the given frequency, which is 3.0. So in other words, let me just make it just for the sake of convenience. Let's do this 3.0 into 10 to the power. This thing can be used as rounded up, 3.0, okay, into 10 to the power 8 meters per second. Okay. Next is over the frequency, which is 3 into 10 to the power 9 meters. Sorry, not the meters, but it's the hertz. And remember that the hertz can also be written as seconds inverse. So 3 into 10 to the power 9 per second. Okay, so seconds inverse. So if you look at it here, now the second inverse and second inverse cancel out. Okay, so you are also canceling out the 3 and the 3. And so once we finish this, we get 1.0 into 10 to the power -1 meters. This is the wavelength. Next, we are going to substitute this into hc over lambda. So the value of h is 6.626 into 10 to the power -34 joules seconds times multiply by, so this piece, these two, this value, this is the Planck's constant times the speed of light, which let's put it 3.0 into 10 to the power 8 meters per second. Okay, so these two multiply, divide them by the wavelength, which is 1.0 into 10 to the power -1 meters. So when you solve this, the meters and the meters cancel out, seconds inverse and the second inverse and the seconds cancel out. So you're just left with the unit of joules. And when you compute this, the answer comes out to be 2. So the value of energy is equal to 2.0 into 10 to the power -24 joules. Okay, so that's the answer. Let's look at the next question. Okay, so here we are given, or we know that E is equal to h nu, and that is the energy of 1 photon. So the value of h is the Planck's constant, 6.626 into 10 to the power -34 joules times seconds. The nu, which is the frequency, is 9.87 into 10 to the power 14 per second. Now per second is the hertz. So these are interchangeable, hertz and per second. Okay, now let's find the energy of the photon using these two values. So E is equal to h nu, and h stands for 6.626 into 10 to the power -34 joules times second. Okay, multiply that by 9.87 into 10 to the power 14 seconds inverse or per second. Okay, now when you multiply the two, this is what you get. Okay, just so for the sake of convenience and calculations, so this is what I did. 6.626, multiply that by 6.626 first, multiply this number by 9.87 and you get 65.39. Okay, next is we're going to look at the these 10 to the power -34 and 10 to the power 14. So this one, when -34 minus the 14, and your answer comes out to be, and we will just keep it as it, we don't move the decimals. So 65.39 into 10 to the power -20. Okay, now this is, remember that this is the, let me get another color. This is the second, and this is seconds inverse. So these cancel out. Seconds inverse and seconds cancel out. So you are just left now with 65.39 into 10 to the power -20 joules. And this is the energy. Energy is equal to 65.39 into 10 to the power -20 joules. Now what we're doing is the question is asking us that what is the threshold energy in kilojoules per mole? Now, kilojoules. So convert this joules into kilojoules. So let's write this down here. Convert the joules to kilojoules. Okay, so we know that 1 kilojoule is equal to 1000 joules. Okay, so now what you do? You're going to take the E, which is 65.39 into 10 to the power -20 joules, and convert that to kilojoules. We know that 1 kilojoule is equal to 1000. 1000 is 10 to the power 3 joules. So when you bring this just keep it as 65.39 into 10 to the power negative 20. And remember that these joules and joules cancel out, and you're just left with the kilojoules. And this into 10 to the power negative 3, this whole thing is kilojoules. So in other words, this becomes 65.39 into 10 to the power negative 23 kilojoules. So this is just the ease of calculations. Now, the question is asking us, find the energy of the photon of aluminum, kilojoules per mole. Kilojoules per mole. Okay, this is how much is the energy in kilojoules per mole. Now, for 1 mole would contain 6.0, sorry, 1 mole would contain 6.022 into 10 to the power 23 electrons. Okay, so electrons. Okay, so 1 mole would contain that. So in other words, E is equal to 6. So let's just do this, 65.39 into 10 to the power 23, negative 23 kilojoules times, remember it's per mole. So, so here we have per mole would be over 1 mole. Let's leave it here. 1 mole contains 6.022 into 10 to the power 23 electrons. Okay, so that's the particles of, obviously, the photoelectric effect problem. So here we have the, what is it, per mole, no? So so here 10 to the power negative 23 and 10 to the power 23, they cancel out, and you are just left with now 65.39 times 6.022, and that is the kilojoules of these electrons, 6 kilojoules per mole. And let's finish this calculations. Okay, so this comes out to be 393.83 kilojoules per mole. Here you can do this, round up. So this becomes 394 kilojoules per mole. So this was a question that related to the photoelectric effect. So when the energy of the photons, this is in problem of photoelectric effect. So here you're calculating the energy of the photon. Okay, let's look at the next problem. So the next problem in 6.4 is related to the Bohr's model. So here we are calculating the energy of the electron in the orbit. So when the electron jumps from a lower energy level to a higher energy level, it absorbs energy, and that energy is, we are going to calculate as shown by the formula E is equal to negative K Z square over N square. K is a constant and has a value of 2.179 10 to the power negative 18 joules. Z stands for the atomic number, and Bohr's model is good only for the hydrogen atom. So we look at Z as the atomic number of hydrogen, and N is whatever energy level it has jumped to. So in this case, N is equal to 6. Okay, so let's just plug in the values. Here we are looking at the energy of the electron. E is equal to negative 2.179 into 10 to the power negative 18 joules times the Z square. And Z square is the atomic number of hydrogen, which is 1. So let's put this here as 1. So 1 square, okay, over n square, and n square is 6. So 6 squared, 6 6 are 36. So basically, when we do the calculations, this is what we get. So when you multiply 2.179 with 1 and then divide that by 36, you get 0.0605277 into 10 to the power negative 18. But converting this to a scientific notation, which means we are going to move this decimal 2 places to the right. And this number is going to be increased by the value of 2. So negative 0, this becomes negative 6.05, and 7 is more than 5. So therefore, 2 is rounded up to 3. So this becomes 6.053 into 10 to the power negative 20, and that is joules. Okay, so that is the energy of the electron when it jumps orbits. Let's look at the next question. Okay, so in this question, we are looking at a situation where the energy and the wavelength of the electrons in transition, you know, in a one electron system, that is a Bohr system. So here we are trying to find the energy of the electron when it moves from energy level 5 to energy level 3. So in other words, the electron is releasing the energy is released in this case, and the wavelength and the energy we need to determine. So there are certain things we already know. We know that the change in the energy when the electron jumps from a lower to a higher, or from a higher to a lower, that change is, you know, whatever the higher level it is, like the initial level to a higher level. So that's subtraction. So E1 minus E2. In other words, the delta E value, the change in the energy, is equal to 2.179 into 10 to the power negative 18 times 1 over n1 square minus 1 over n2 square. So that is the initial where it was, and this is the final where it is. So that's the initial and the final. So anyways, now we will see the wavelength is equal to hc over E. H is the Planck's constant. The value is already known, 6.626 into 10 to the power negative 34 joules times seconds. And C is the speed of light, which is 3.0 into 10 to the power 8 meters per second. So let's find this. Just using these formulas, let's find these values. Oh, so, you know, guys, there's something I missed in this problem, and that is that we are talking about helium and not hydrogen. So we will have to change the value of the Z. Okay, so here we are. The question here is of the helium ion, where Z is equal to 2, and that's something I forgot to mention. So let's put it here, that Z, this is given in the question, that the Z, that is the atomic number, is equal to, for the helium ion, and that is equal to 2. Okay, so with that saying, now we have the situation where we will have to, first of all, in order to bring in the change in energy, we will have to look at the energy when the energy is when the n is equal to 5, so the energy associated with that, and when the energy is when n is equal to 3, so the energy associated with that. Okay, so we know that E, value of E, is equal to negative k z square over n square. Okay, so negative k z square over n square. So that's one thing we know. We also know the value of k, which is 2.179 into 10 to the power negative 18 joules. This is also known. Okay, so yes, we know the value of H, which is the Planck's constant, and we have also already talked about the value of C, which is the speed of light, and then the relationship, you know, of these two to find with the energy to find the wavelength. So we will look into that. Now let's look at, first of all, the energy that is associated with the energy level 5. So that is E5. E5 is equal to negative K Z square over N square. So now let's plug in the values, which is negative 2.179 into 10 to the power negative 18 joules. So that is the value of K, times the Z squared. Z squared is 2, and 2 square. 2 square would be 4. So over the N square, and N square in this case is 5. So N is 5, so 5 square. So 5 square would be 25. So negative 2.179 into 10 to the power negative 18 joules times 2 square would be 4 over 5 square is 25. And here we have negative 0.348 into 10 to the power negative 18 joules. And just leave it like that. Don't move the decimal. Okay, let's look at now the energy that is associated with the level 3, which is negative K Z square over N square. And here you have negative 2.179 into 10 to the power negative 18 times 2 square, because still it's helium, over, so let's just keep it here, over the N square in this case is 3. So 3 times 3 becomes 9. So let's put in these numbers again. 2.179 into 10 to the power negative 18 times, let's put this here. This is joules, and joules times 4 over 3 3s are 9. Okay, so now you have negative, when you solve this whole thing, you get 0.968 into 10 to the power negative 18 joules. Now let's look at delta E, which is the change in energy when the electron jumps from E5 to E3. So in other words, this is emitting radiations. So here, in this case, the E5 value is negative 0.348 into 10 to the power negative 18. Okay, so that's one number. Minus, another minus 0.968 into 10 to the power negative 18. And both of them are joules. So when you subtract, and this whole thing becomes 0. Positive, of course, 0.620 into 10 to the power negative 18 joules. Excuse me. And now you can move the decimal to give it a scientific form, which is 6.20 into 10 to the power negative 19 joules. So that is the change in energy, or the value of the energy that is emitted when the electron jumps from a higher energy to a lower energy. So this is what we have. So this answer relates to 6.198 into 10 to the power negative 19 joules in the book. Now the next point is, the next thing that we're wanting to find is the wavelength, and that wavelength is in meters. So we already found the energy in joules. So for the wavelength, we will use HC over E. So is H wavelength is equal to H times C over E. H is the Planck's constant, and the value given here is 6.626 into 10 to the power negative 34. So let's put this number here, 6.626 into 10 to the power negative 34, negative 34 joules times seconds, sorry, joules times seconds. Okay, so this is one piece, times 3.0 into 10 to the power 8 meters seconds inverse. Okay, over the value of energy, and the value of energy is 6.20 into 10 to the power into 6.20 into 10 to the power negative 19 joules. Okay, so negative 19 joules. Now, if you look at these units, so joules and joules cancel out, seconds and seconds inverse cancel out, and we are just left with meters. So now what you do, you take 6.626 times 3 divided by 6.20. So let's see what we get. So here you see that 6.626 times 3 divided by 6.20 gives you 3.20. And then we have 10 to the power negative 34. And we have 10 to the power 8. And then when 10 to the power negative 19 comes on the top in the numerator, it becomes a positive 19. So positive 19 plus 8, and then minus the 34 is going to give you, sorry, I got knocked out. Hold on. Okay, so we see that the wavelength then comes out to be 3.20 into 10 to the power negative 7 meters. And that's the answer. Okay, let's look at another problem. And that's calculating the wavelength of a particle. That is 6.6. Okay, so this problem 6.6, this relates to the de Broglie's equation, or de Broglie's principle, which stated that the electrons actually exist as waves and electrons can also exist as particles. So here, when we are talking about particles, that means there is a motion, or we're trying to determine, the movement of the particle with respect to its velocity, the speed, and then the mass of the particles. And we have the Planck's constant, 6.626 into 10 to the power negative 14. Now, this piece right here, you see kilograms, meter squares per second. This relates, this is actually the joules. So joules is equal to kilograms meter square per second, or this relates to kilograms meter square seconds inverse. Okay, all right, so that's one piece. Then comes the next is the value of M. M relates to the mass. M is the mass. And the mass given to us here is, calculate the wavelength. And we need to find the wavelength, calculate the wavelength of a soft ball with a mass of 100 grams. So mass given is 100 grams and traveling at a velocity. The velocity, the speed with which this soft ball is traveling is 35 meters seconds inverse. Okay, so the speed of the soft ball is given and the mass is given. So here are a few things. We need to convert the grams to kilograms so that we have the same units. So let's do it. 100 grams times 1 kilogram over 1000 grams. Okay, so this is going to be, this is the mass now in kilograms. That's one piece. And here we have to find the wavelength. So this becomes 10 to the power, so let's just put it here, 1.0 into 10 to the power negative 1 kilograms. This is your, here, find the wavelength. Okay, so rest is, we just have to plug in the numbers, and wavelength is equal to H over M times V, that is mass times velocity. So here is 6.626 into 10 to the power negative 14, okay, kilograms times meter square times seconds inverse over the mass is 1.0 into 10 to the power negative 1 kilograms. That's the mass, times the velocity is 35 meters per second, or seconds inverse. Okay, so now we see here that the seconds inverse and the seconds inverse cancel out. Meters and this meter square cancel out, and we're just left with the meters. And then kilograms and kilograms cancel out. So all these units cancel out. This is an important thing. Next is, we're just going to take this 6.626 over 1.0 times, so over 35. So let us see what we get here. Okay, guys, my apologies. It's getting very late here, but anyways, so I actually made a little typo error, and that was here I put negative 14. So this is Planck's constant. It should be negative 34, 6.62 into 10 to the power negative 34. And that's the number you take and you put it here, plug in here. And when you solve it, you should get 6.626 into 10 to the power negative 34 times, now here this was 10 to the power negative 1. So when it's inversed, it becomes 10 to the power, positive 1. And when you multiply the whole thing, it becomes 0.189, sorry, it's 1.89. 1.89, or that's equal to 1.90 into 10 to the power negative 34. And since this is a wavelength, this is meters. And this is like indeed very, very small. Now we're talking about softball, which is, it's practically impossible. So this only applies to this relationship, and this de Broglie's equation only applies to the particles that have very small mass, and then only it makes sense. So anyways, this is the 6.6, and now let's look at the next problem. Now let's look at the quantum numbers. So for there's some rules here. So n stands for the shell, and the value of L, let's do this, L, and then the name, and we have the M, and then we have the number of orbitals, and we have the number of electrons. Okay, so the name of the subshell, the L represents the main energy level. L is the subshell, and then this is the orbitals and the electrons. So that's one piece. Now keep this in mind that these one second, N represents the principal quantum number. Let's put it here, above here. N is the principal quantum number, and principal quantum number is the main energy level. So quantum number, and that is the main energy level, the bigger one, energy level. So keep this in mind that now we are working on locating the electrons, or giving a placement to the electrons in the energy level outside the nucleus. So N is actually, it relates to the size and the energy of the energy level. okay, of the shell. And the values of n go from, 1, 2, 3, 4, and so forth. Okay, so that's one piece. Then comes the next one, L. So what does L stand for? L is the angular momentum. So angular momentum relates to the shape. Okay, so this is the shape of the orbital. So in other words, in 3-dimension, shape of the orbital, the place where the electrons are found. And their value is, the value of ranges from L is always n-1. So in other words, it can be 0. So L is equal to 0, 1, 2, 3, and so forth. Okay. Next is ML. Now ML is the magnetic quantum number. Magnetic quantum number. And what does a magnetic quantum number deal with? It deals with orientation. Orientation is like in 3D. Like what is the orientation of the orbitals, like length, width, and height. And so the values of these are, the values of ML range from -L, 0, and +L. Okay. And then, so we will look into this more, but basically this is the orientation of the orbitals. And now comes the last piece, which is the MS, or the spin quantum number. So MS is the, let's put it here, MS is the spin quantum number. And what does this deal with? It deals with the, the movement, the upward and the downward movement. So basically the clockwise and the anti-clockwise. So clockwise spin is +½ and anti-clockwise spin is -½ Okay. All right, so we have these are the very basics of these guys. So here we are looking at now the, so in other words, let's look at now the, this would be the, this is L, this is ML, and this is going to be the number of electrons and their spin. So this would be related to MS. Okay, so this is ML, and this is L, and this is N. Okay, now let's do this. So when the value of N is equal to 1, so in other words, first energy level, the number of L is equal to, remember, it's the n-1. So 1 minus 1 is 0. So when N is equal to 1, let's move this here because I need some space here. And then this one, sorry. This is, give me 1 minute. More, because we need some, this is going to take a lot of space. And then the number of electrons is, okay. So we have when N is equal to 1, L is equal to 0, the name is 1s, and ML is 0, the number of orbitals is 1, and the number of electrons are 2 electrons, and one is spinning upwards and the other is spinning downwards in the orbitals. Okay, that's one thing. Next is when N is equal to 2, then L is equal to 0 and 1. So 2 values of, in this case. And what are their names? This is 2s and 2p. Okay, then ML. So the ML for 2s is 0, but 2p would be -1, 0, and +1. So number of orbitals in the first cases, and the name also, let's just put their name also here. Name of the orbitals is, so this would be 1s, and this one is 2s, and here the orbitals are 3, and the name is 2p. Number of electrons are 2 here, number of electrons are 6. So these guys are spinning like this. These are spinning in 3 orbitals like that. Okay, so these are the orbital diagrams also. So these are the 6 electrons in 3 orbitals. Okay, so let's put this guy a little bit here so they don't overlap. Okay, next is we are looking at the third energy level. So the number of L is 0, 1, and 2. The names of these subshells is 3s, 3p, and 3d. The ml values are 0. This one is minus 1, 0, plus 1, and this one is minus 2, minus 1, 0, plus 1, and plus 2. And here the number of orbitals is 1. Here the number of orbitals is 3, and number of orbitals is 5. The names are, let's move this thing here, 1, 3, and 5. 1, 3, and 5. The names are 3s, 3p, and 3d. So now the number of electrons are 2, 6, and 10. And how are they located? Like this: 1, 2, 3, 4, 5, 6. And these guys are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Now we have, in this case, you can see these are the orbitals where these electrons are located. So you can see 6 electrons in the p orbitals and 10 electrons in the d orbitals. And each orbital is occupying each orbital has a maximum of 2 electrons. Similarly, when n is equal to 4, then L is equal to 0, 1, 2, and 3. Okay, now when you have the subshell name, so this is 4s, 4p, 4d, and 4f, and their ml value is 0. This one is minus 1, 0, plus 1. This one is minus 2, minus 1, 0, plus 1, and plus 2. And here in F is minus 3, minus 2, minus 1, 0, plus 1, plus 2, and plus 3. Okay. Now the names are of the orbitals. This is 4s, 4p, 4d, and 4f. And as you can see that the S will always have 2 electrons. So the number of orbitals, I forgot to put that piece here. Just give me 1 minute. Make this small. Okay, so here something that I forgot was the number of orbitals. So the number of orbitals are, so here we have 1, 4p will have 3, 4d will have 5, and 4s has 7. And these 7s, the names are 4s, 4p, 4d, and 4f. So number of electrons, 2 on 4s, 6 in 4p, 5 in 4d, and 10 in 4d, and 10 in 4d, and 14 in 4f. And so, you know, the spinning is the same as above. So as you can see now, the first energy level The first energy level has only 2 electrons. The second energy level has 2 and 6, 8. The third energy level has 2 plus 6 and then this 10. So this becomes 18. And the last one, the 4F, will have a maximum of 32 electrons. Okay, so that's the deal with these quantum numbers and the actual, energy levels. So now if you have a question, so if you put up a chart like this, if you can make a chart like this the way I have done, it will be just easier. You'll have to do this anyways. So now comes the question from 6.7. 6.7, and the question is asking, identify the subshell in which the electrons with the following quantum numbers are found. So we need to find which subshell will have the electrons with the quantum number n is equal to 3, L is equal to 1, L is equal to 1. So this is A. So which one is that? So let's go and locate this. N is equal to 3 and L is equal to 1. So N is equal to 3 and L is equal to 1. So we are looking at the name of that subshell is 3p. So the name is, so this is present in 3p. Okay. Next question is, so you just have to do this diagram, the what I have written just now, just have to do this on your own. Okay. The next question is, when n is equal to 5, then what is it when L is equal to 3? So which one is that? So n is equal to 5 and L is equal to 3. So same way you're going to do this. So n, so let's do this here. N is equal to 5. Then L is equal to 0, 1, 2, 3, and 4. Remember, it's always one less. So I'm going to just make this small. Make this small. Okay, it's just a matter of space and it's not letting me. Why? Just come on, move. Okay, maybe it doesn't want to do it. Okay, let's do it on the different page. So here we have n is equal to 5. L will be 0, 1, 2, 3, and 4. And then you have, which one is it? So we talked about this thing would be 4s. So this becomes 5s, 5p subshell, 5d, and 5f, SPD and F. So so the question is, which one is when L is equal to 3, N is equal to 5, which one is that? So we are looking at N is equal to 5 and L is equal to 3. So the answer is 5F. 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 So this is how you will have to do these. So let me make this small now if it will allow me. It's not letting me make it small. So anyways, this is how this is done. Sorry, this is how this is done. Okay. So anyway, so you can do the other one. When N is equal to 2, L is equal to 0. Which one is that? So this one we already did. N is equal to 2, N is equal to 2, and L is equal to 0. So which one is that? That is 2s, as you can see. So the answer is 2s. C is N is equal to 2, N is equal to 2, and L is equal to 0. So from the chart, we see that is 2s. So some of the species, you just have to memorize. Okay. Next is the so the question is 6.8, and that is 6.8, 6.8. Now the question is, if a shell contains a maximum of 32 electrons, so a shell is containing 32 electrons maximum. Then the question is, what is the principal quantum number? So the principal, so the value of n is equal to what? So we have already seen that the value of n is equal to 4, as we have seen above. Okay, so there is a little cheat sheet here, and I'll write down some of the little, formulas for that. Hold on. So here we have some of the formulas that you can consider. One of them is, let's put it here. One of them is the tricks, it's like tricks. So you don't have to go through this whole process, but you can do these tricks that n squared is equal to the number of orbitals. So whatever the value of n is, the number of orbitals relate to that. For example, let's look at this. If we have n is equal to 3, okay, then the number of orbitals are going to be total number of orbitals is equal to 3 square. That is 3 3s are 9. And we can see this here. N is equal to 3. N is equal to 3. And do we have 9 orbitals? 9 orbitals. So 5 plus 3, 8 plus 1, 9. Okay. When we have 4, n is equal to 4. So 4 times 4 is 16. So the number of orbitals are 16. 7 plus 3 is 10, plus 5 is 15, plus 1 is 16. So that's the little thing, you can, check that. So let's just do this. When n is equal to 3, then number of orbitals is equal to 9. And what is their name? The name is, which are the names? So 3s, 3p, and 3d. So d has 5 orbitals, p has 6 orbitals, and wait a minute, 1 second. 5, 3, and 1. Yeah, sorry, I was looking at the electrons. 5 and 3 and 1 orbital. So when you add these, this come out to be 9. So that's 9 orbitals. Okay, so that's one piece. Next is the maximum number of electrons that can be had. So this is one piece. Next is maximum number of electrons. And the formula for that is 2 times the n square. And 2 times the n square is what? Like, for example, when n is equal to 2, then the maximum electrons is, then the number of electrons, the maximum that can be held is 2 times 2 square. So that means 2 times 4 is equal to 8 electrons. And as you can see here, 2 is here, 2 is here, and then these 8 electrons come out, 2 and 6. So that's in 2s and 2p. So if you have n is equal to 4, then the maximum number of electrons would be 2 times 4 square. 4 square is 16, and 2 times 16. So 16 times 2 is 32 electrons. And you've already seen this in this chart here, 32 electrons, how they place. Okay, so that's one thing. Next is the other one is the degeneracy rule. Degeneracy is like when the orbitals have the same energy levels or same energy. So degeneracy is equal to 2L plus 1, and that is the 2L plus 1. So for example, you have like 4p orbitals, 4p orbitals where n is equal to 4, right? And so L is equal to 0, 1, 2, and 3. So that's the S, P, D, and F. Okay. So if they're saying that 4p would means the 4p would be degeneracy is 2 times the L. I'm forgetting this one. I need to look at this one. I'm not sure about this one, but maybe a little bit phasing out. So hold on to this, okay? Now we have the last part, I believe, or we are done. Okay, working on the quantum numbers, we already did that one. Okay, let's do this last part. The last question is working with the quantum numbers, and that is 6.9. So we did 6.8, 6.9. So again, the chart, if you make it on your one side, it'll help you, okay? So 6.9 is how many orbitals have, how many orbitals, have L is equal to 2, L is equal to 2, and N is equal to 3. Okay, N is equal to, or rather, N is equal to 3 should be first, N should come first. N is equal to 3 and L is equal to 2. So let's look at how many orbitals have that. So how many orbitals have N is equal to 3 and L is equal to 2. So let's look at, let me bring this number. N is equal to 3. So this one, and L is equal to 2. So this one. And in that, this piece and this piece applies to 3D orbitals. So all these will have, all these guys, all the 3D orbitals will have the N is equal to, so I'm going to just put this here. Look at the table above with star marked in pink color, with the star marked in pink. Sorry, star marked in pink. Okay, so here you see that when N is equal to 3, then L is equal to, again, I can write the whole thing here, is equal to 3, then L is equal to 0, 1, 2, and 0, 1, 2. And that becomes here, this is 3S, 3P, and 3D. So the question is, how many? So 3D has 5, right? 5 orbitals, 1, 1, 2, 3, 4, 5. And in these orbitals, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 electrons. So 3D and N is equal to 3. So these are the ones we are talking about. And here. All right, so this finishes this part till here. Next is, there's plenty of videos I've made on electronic configuration. a very big one actually, explaining a lot of details. So I am not going to do the electronic configuration right now, but if there is time, then I'm going to do it. But in general, I will just hold on to this part till here. All right. All right. Thank you for watching. Bye-bye.